This is the acetal, ketal, and carbohydrates slides commentary. So in this set of slides, we're going to be focusing on naming as well as practicing reactions involving acetals, ketals, as well as hemiacetals, hemiketals, and cyclical hemiacetals, ketals. We'll then go ahead and go directly into the biochemistry chapters, starting with carbohydrates. So in these set of slides, I do jump around from chapter 3, 4, and 7. So I apologize ahead of time. But I think I've designed it better than the book has outlined it. So please go by these slides as you study for the upcoming material, and then use the book as reference. So to begin, in this slide we have 4 categories. I'll go ahead and I'll use the yellow highlighter. We have the hemiacetals, hemiketals, acetals, and ketals. Now, what we've done is we've given carbons who have either alcohol or ethers on the same carbon. We've given them special names, which is hemiacetal, hemiketal, acetal, ketal. So just like we gave the carboxylic acid its name because there was a carbonyl group and a alcohol, in this case we give them these names for the carbons that I'm highlighting right now. We give them these special names based on whether they have 2 ethers or they have a combination of alcohol and ethers attached. So that's a lot of verbose commentary. So let me get into some actual examples. Let's go ahead and focus on the top left and right slide. I'm circling it with my red pen. These are hemiacetal and hemiketals. You'll notice at the very top, for each of the carbons, they have an alcohol attached. So make the mnemonic connection that hemihydroxy. So make that particular mnemonic connection. Hemihydroxy group. Hemi and hydroxy group. So those are the big differences between the hemis and then the traditional acetal and traditional ketals. The next thing you want to go ahead and take a look at, let me go ahead and erase these little comments here. The next thing you want to do is take a look at, is there a hydrogen that's directly attached to the carbon? So in the upper left hand quadrant I circled a hydrogen, and notice how it's directly attached to a carbon. If you look in the lower left hand quadrant, there's a hydrogen directly attached to a carbon. So it turns out that if you have hydrogens directly attached, these are acetals. If you take a look at the right examples, and I'll go ahead and I'll color them in purple. The ketal carbon and hemiketal carbons, there are no hydrogens that are directly attached. Instead, there's carbons on each side. So as we get into reactions, another thing you'll notice is whenever we have a aldehyde, which is a primary carbon and has a hydrogen directly attached, aldehydes tend to form acetals. And just as you've guessed it, ketones tend to form ketals. So that's another way of remembering it. Alright, so if you take a look at the bottom two, notice they have 2 ethers that are directly attached. 2 ethers that are directly attached. So acetal and ketal always have 2 ethers, as I've just highlighted. If there is a hemi, then that means there's a hemihydroxy, aka alcohol group, that's attached on top. Let's go to actual examples. So let's focus on the one that I'm circling to the upper left-hand corner. This is a hemiacetal. It's an acetal because it automatically has a hydrogen that's directly attached. It's a hemi because hemihydroxy, one of the functional groups, is a alcohol group. Let's go over to hemiketal. It again hemi because there's a hydroxyl group or alcohol directly attached, and it's a ketal because it's a middle carbon where there's no hydrogens directly attached. Let's go to the bottom. For the acetal, again, acetal because there's a hydrogen that's directly attached. It's not a hemiacetal. There's no alcohol directly attached. There are, however, two ethers that are directly attached. Two ethers. So traditional acetals and ketals always have two ethers. Let's finish up on the example to the right. Two ethers, so no hemi. And it's a ketal because there's no hydrogen that's directly attached. It's a secondary carbon or middle carbon, as we see here. I've given you an alternate example. This is an example of a cyclical hemiacetal. Now this one's a little bit tricky. Let me go ahead and match up each of the groups that I just talked about in the other example. So let's go ahead and compare these two together. So we have a hydrogen that's directly attached, as we have in both of them. So that's our first criteria. We have a hydroxy group that's directly attached to both of them. And finally, we have a ether that's also there. In this example right here that I'm circling, here's our OR group. And then if we look over here, here's our OR group. So even though it's in a nice heterocyclo alkane, let me say that again. Even though the ether is in a nice heterocycloalkane, it's cyclical. It's still technically a OR group or ether group, cyclical ether, if you will, and therefore it's still a hemiacetal. Let's go to the example to the right over here. Again, this is a secondary or middle carbon, no hydrogen directly attached, so it's automatically in the ketal category. Hemihydroxy, so it has hydroxy, and then here's the OR group right here. Let's go over to the cyclical hemiacetal. There's our hydrogen. Here, cyclical acetal. So let me say that again. Cyclical acetal. There's our OR group. Here's our other OR group, our other ether. So one's non-cyclical, the other one is cyclical, but it still counts as a double ether, so therefore it's an acetal. Over here, you can see the same thing, double ether, and it's a ketal. And this is a middle carbon, no hydrogen directly attached. So, beat that to death, ketal. Here are the reactions you have to know. So in this first one, we're going to be forming a acetal. So the other thing we're going to be forming is a hemiacetal. So even though it says, by the way, up here it says formation of acetal, it's actually a combination of acetal and hemiacetal. I should point that out. If you start off with a aldehyde and you add in a alcohol, it's going to form a hemiacetal always. So again, if you start off with an aldehyde and an alcohol, it's going to form a hemiacetal. Please make the mnemonic connection aldehyde acetal. Aldehyde acetal. So in this case right here, here's our alcohol. I'll go ahead and try to color code this if I can. Here's our hydrogen right here. This hydrogen is going to directly attach with a pi bond, this other pi bond from the carbonyl oxygen. This hydrogen is going to combine with that pi bond, and it's going to form this OH group. The rest of the alcohol, it's going to do what we call a backside attack. It's going to, if the carbonyl oxygen is the front, then the back of the carbon is the trunk, the backside. So we call this the backside attack. And in this case right here, it forms an actual ether. So let's see the next example. Here's an actual example of a molecule I could give you. Here we have the carbonyl group. One of the pi bonds is going to form a brand new alcohol. And then I might as well use the color blue since I have the colors in front of me. And then the remaining oxygen, again, backside attack, and is going to attach, thereby forming a brand new ether connection. Now, I put these next to each other. We've created a hemiacetal. Now, if this product over here is in a different reaction and is actually the reactant this time, again, so if we're starting off with the reactant as being a hemiacetal, then this is the reaction. The hydrogen that's right here, I don't know if we can circle this right here. Here is the hydrogen. It's going to do something really weird. It's going to go ahead and combine with this hydroxyl group, and it's going to form a brand new water molecule. The remaining portion, the OR, is going to go ahead and fit in the same place that the previous alcohol was located at. So basically when that hydroxide comes off, the alcohol comes off, then it leaves an open space. There are only 3 bonds on the carbon, which is very unstable for the carbon. So the remaining OR is going to connect and form a brand new covalent bond, and it will form this one right here. So let's see this one more time. In this case right here, and in this example, our methanol, the hydrogen is going to come off and combine with the alcohol, aka hydroxy, and it's going to form a brand new water molecule. The remaining portion is going to attach to the carbon to make up a brand new bond, which is what we see here. Now, even though we're starting off with a ketone instead of an aldehyde, the reaction is the same. So just as in the aldehyde, and notice the only difference between a ketone and aldehyde is this group right here. In the previous slide, we had a hydrogen that's directly attached. This time we have a R group that's attached. So this carbon's a secondary or middle carbon, middle-ish carbon, so to speak. But it's this exact same reaction. So in this case right here, the hydrogen comes off, and this pi bond right here is going to come up and combine with this hydrogen. This leaves only 3 bonds on this carbon, so then this oxygen right here, which I'll highlight in blue, is going to go ahead and combine with this carbon. So we have another reaction over here that we can see. Let me go ahead and continue playing with the colors. This pi bond is going to come up, combine with this hydrogen, hydroxyl group. So at this point you should be seeing the pattern. And then this oxygen is going to do a backside attack, and now it forms a brand new ether group, or ether functional group, aka we now have a ether branch. And there is our product. Now, let's say we actually started off with a hemiketal as a reactant. So in this case, we're starting off as a hemiketal as a reactant. So just as we had in the previous example, the only difference between this one and the other one, the hemiacetal, is instead of an R group, we had a hydrogen. But the overall reaction was the same. So in this case, the bond right here is going to the bond is going to break, and it will form the electrons will form a brand new covalent bond to this hydrogen, creating a water molecule. Now that this bond is missing on this carbon, there's only 3 bonds instead of 4, so a brand new bond is formed with the remaining OR group, creating a brand new ether. So you should see the pattern here. Here's a nice example, exact same pattern, and I'll still circle them, hydrogen, water, and then remaining OR group bonds to the carbon, forming a brand new ether branch. So now it's a double ether, and because it's a middle secondary carbon with a double ether, it's a ketal. So let me go ahead and give you 2 random examples. I'll go ahead and do it on the whiteboard. So I could give you a problem like this, and this is just like the handouts that I've given you. I could give you either a name, or I can give you a starting sketch and ask you to predict the products and name the products. So I could give you something like this. This is a reversible reaction. It goes both ways. In this case, the oxygen is going to combine with the hydrogen, and this bond right here is going to form a new bond in the back of the carbon called the backside attack. And now we have this as our final product. This right here, it's classified as a hemiketal. Hemiketal. And the proper name for this product right here is a 2-hydroxy. Actually, I take that back. I need to alphabetize it. 2-ethoxy, 2-hydroxy propane. Okay, so that one's pretty straightforward. Let's go ahead and do another one. I could give you something like this and say ethanal, and that is an A. It's an ugly looking A, but it's an A. You can put 1 ethanal. It's kind of redundant because 1 is implied, or you can just write ethanal. Ethanal plus 1 ethanol. And if you see something like this, then you'll need to predict and name the products. It would be very helpful to go ahead and draw the structures first just to see what we're looking at. The line angle for this one is this right here. Careful on this one. This is a ethanal. Notice it only has 2 carbons right there. There's a carbon, there's a carbon, and then this is a hydrogen. So notice that it'll create some sort of acetal. It could either be acetal or hemiacetal, but let's investigate that. So here is our alcohol, ethanol, and so as far as the, oops, let me scratch that out. As far as the answer goes, this bond right here, let me recreate that one. Recreation time. So I'm just going to go ahead and sketch. You can rewind it if you need to go ahead and take a look at the original name. But it was a ethanal plus a alcohol. And this pi bond formed a brand new bond to, and I messed up again. Let me go ahead. See if I can get this right. Aha! Okay. There we go. So this bond right here is going to combine with this hydrogen, and it's going to form a brand new alcohol. There we go. Now, the remaining portion is going to do the backside attack. We have this structure right here. As far as the actual name for this goes, this can be kind of tricky. In this case, I'm going to go ahead and circle where the parent is. This is the parent right here. So the parent on this one would be ethane. Now I'm going to go ahead and circle the 2 groups. So in this case, this would be 1 hydroxy. Oops, no, it wouldn't. It would be 1 ethoxy, 1 hydroxy ethane. There we go. Because it has to be alphabetized. E in front, and then H. So careful, those can be tricky. I could also ask you to name the original molecule just for the heck of it. Although I did give you the answer on this one already. So this one was 1 ethanal. Notice that's an ugly looking A, but it's an A. Let me rewrite it. There's a nice pretty A. And this one over here is a 1 ethanol. Notice it's O. So O for alcohol, A for aldehyde. So I think I've beat that to death. So be sure to practice with the study guide. Be sure to practice with the examples also in your in-class assignment. So let's go ahead and move on. This right here is a molecule. Notice there's not 2 molecules. There's only 1 molecule here. 1 molecule here. The only thing left is the catalyst. I'm going to even tell you what catalyst it is. It could be sulfuric acid. or it could be phosphoric acid. We just like to use H+ because we don't want you to focus on that. What we do want you to focus on is notice how on one side of this molecule you have a aldehyde. On the other side of the molecule you have a alcohol. Basically, if we think of this as a snake, here's the head, here's the tail. The tail is going to wrap around itself and basically react with itself. It's going to form, in this case, a cyclic structure. I also say the word cyclical. And it could be a cyclical hemiacetal or it could be a cyclical hemiketal. And I could test you on either one. So to figure out how many carbons are going to be in the cyclical structure, here's my advice. And this is not for naming, this is just for sketching the structure. My advice is to go ahead and start counting the carbons. 1, 2, 3, 4, and then count the oxygen on the alcohol. Again, this is not for naming. I did not teach you the names. This is only for sketching your product. And that's the only thing I will test you on is sketching the product. The UPAC rules for naming cyclic ethers can be really tricky, and I'm not going to be testing you on that. We do have future cyclical ethers. You have to memorize their names for biochemistry molecules, but those are common names, and those are just straightforward memorization. For these, sketch only. So we counted carbon 1, 2, 3, 4, 5, and then the alcohol is the fifth. You then go ahead and draw a line or condensed structure, and you account for in a circle a cyclical structure. This is a heterocyclic molecule, and again, count it. Carbon 1, 2, 3, 4, and then cyclical. Here's my cyclical ether right here. On carbon 1, the aldehyde always forms a alcohol. And the original alcohol, which I'm circling right here, the original alcohol always forms the ether. So in my example to the right, here I have a line angle structure. The oxygen is going to wrap around itself. The alcohol is going to wrap around itself and form an ether. The aldehyde is basically going to, and I'll draw this in a separate color. Maybe I'll use blue. The carbonyl group is going to go ahead and, or the aldehyde is going to go ahead and grab a hydrogen. It's going to form a alcohol. So let me say that one more time. Matter of fact, I'm going to go ahead and use the colors that you see over here in these arrow pushing arrows. Let me say that one more time. So the tail is going to wrap around. The aldehyde is going to form the alcohol by grabbing off this hydrogen, and the alcohol is going to form a ether. Here is the structure that you're required to draw. The hydrogen here is optional. It's a good habit to get into to remind yourself whether it's a cyclical hemiacetal versus a cyclical hemiketal. The hydroxyl group you definitely do need to draw. So let's go down to this hemiketal example down here. Again, the tail is going to wrap around itself. The alcohol is going to wrap around, and the oxygen is going to form a new ether. The ketone in this example is going to pick up that hydrogen from the tail, forming a alcohol. Notice it's a ketone, so therefore it's going to form a ketal. Because we have an alcohol and a cyclical OR group. We have an alcohol and a cyclical OR group. This is a hemiketal. Notice you do have an extra CH3 off to the side that we have to draw. And here is a subsequent example. So let's go ahead and move on. We can go in the reverse direction, starting off with a acetal. Notice automatically I identified it's an acetal versus a ketal by that hydrogen that's directly attached. We can go in the opposite direction, and by adding in water, we can break these bonds. We can break these bonds to form a brand new aldehyde. So keep in mind, this is a reverse reaction because we're converting back to an aldehyde and ketone. Because we're using water, one way of expressing water is to say the word hydro water. So because we're using water to break these bonds right here, break the CH3 and the OCH3, we say it's hydrolysis. Lysis means to break. So this is called a hydrolysis reaction. A hydrolysis reaction. We have an acid catalyst that can be present to speed things up. And notice the names. If this is a acetal, it's going to create a aldehyde. And then you have a leftover. You have two leftover water. You have two leftover alcohols. So let me say that again. You have two, not one, but two leftover alcohols. Let's go ahead and show you how this works. The best way to show you is to break up water into a nice Lewis structure. Now, what's going to happen is the oxygen from underneath of this ether, this oxygen is going to go ahead and combine with this hydrogen right here. It's then going to form a brand new alcohol. In this case, it'll form one of the alcohols. The leftover let me go ahead and erase that. Let me go ahead and highlight this part right here. The leftover alcohol, aka hydroxyl group, is going to go ahead and actually combine with part of the top ether. It's then going to form the other alcohol group, CH3OH. Rather than write two alcohols, we simply add a coefficient in front and say the number 2 for two alcohols. So in this example on the bottom, HOH, here we have the first hydrogen combines with the entire OR group from the ether, and it forms one of the alcohols. In this case, because the ether or the ether functional group is an ethoxy, then it will form an ethanol, CH3 CH2OH. The remaining portion, the remaining alcohol, is going to combine with only this part right here, the R portion of the original ethoxy. The R portion of the original ethoxy. It's then going to form the second alcohol. Hence, we have two alcohols that form. Now, in both of these examples, I made a big deal about it only on the top ether, only combining with this R group right here. Keep in mind, it takes the R group, but it leaves the electrons in the original covalent bond. So this is going to come on down and form a brand new pi bond. Consequently, we now have a aldehyde. Let's go up to my other example. I talked about how this R portion of the original ether is going to combine with the alcohol. So therefore, this the electrons in this former bond is going to come down, forming a brand new pi bond. And it can do that without violating the 4-bond rule because this entire OR group had already left. Consequently, it forms a double bonded carbonyl group, and because it's a primary carbon, it's an aldehyde. Let's go to the next example over here. Here we have a ketal. It's the exact same process as the acetal hydrolysis. So in this case, it's easier if I just break it up into a HOH Lewis structure. On the bottom, the entire OR group is going to come off. The bond itself, by the way, if I haven't mentioned this already, the bond itself is also going to leave, combining with the hydrogen. And it's going to form a brand new ethanol. So it'll form one of the ethanols. Oops. Pushing the wrong buttons by accident. I'm sorry. Alright. So let me draw this again. Let me say this again. The entire OR portion, including the electrons in the covalent bond, is going to combine with this hydrogen, forming one of the alcohols. The remaining portion, OH, is going to combine with only the R portion of this top ether, aka the top ethoxy branch. So in this case right here, it's going to form the other alcohol. Consequently, we just write it as the number 2 because that implies that there are 2 alcohols that are formed. So, because only the R portion that left, and I didn't, in this example right here, you can't see the covalent bond in between, but the electrons in the covalent bond in this one come down to form a brand new pi bond, forming a carbonyl group. And because this carbonyl group is on a secondary middle carbon, it's a ketone. We see the exact same process in the bottom one. Well, let me start with the bottom one down here. So in this case right here, the OR group, including the pi bond, is going to combine with this poorly written hydrogen. The remaining portion is going to combine with this ugly looking alcohol group, forming the other alcohol. And then finally, and here you can visibly see the covalent bond on the reactant molecule. You can see the covalent bond. And because that R group is no longer there, this bond, these electrons in this bond is going to come on down, forming the pi bond in this carbonyl group. We then have the final structure, which is going to be called a 2-butanone. So you're responsible for predicting the products, naming the products, So careful on this one. Let's just go ahead and come up with a quick example showing you the line angle of how I could give it to you. Let me go ahead and use my white screen. So I could give you something that looks like this. Notice if there's no hydrogen here, it's automatic. I'm going to go down, set it to the right, and we need to add one water molecule. Okay. 1, 2, 3. Okay. So in this case right here, it's going to go ahead and form a ketone. This would be known as a 4-heptanone. Keep in mind, I could give you a starting instead of a starting ketal, I can give you a starting acetal. And it may look something like this. So I'm going to do some minor video dental work. Let's see. So what I did was I changed the parent. I made it a primary carbon that we find all of our functional groups on, or a N carbon, so to speak, represented by this hydrogen. And now the proper name for this is going to be called a 2, not a 2, a 1, 1 ethanol. Okay. So starting off again with a acetal, it will create a aldehyde in the acetal hydrolysis reaction. Let's please move on. Okay. So that concludes the acetal, hemiacetal, ketal, hemiketal, and then the cyclical acetal ketal, as well as the hydrolysis of a ketal acetal. Yeah, so we end here in this commentary. Run while you can.